Thanks again. And I'd just like to tell you, Andrei, how beautifully this thing is organized. And what I really like is the personal touch that you guys bring to the conference. This is one of the best conferences I've ever been to. Thank you. So, is there anyone in this room who's reading my blog? Okay, so this is like the morning exercise. For those of you who don't know me yet, I'm a grumpy old man who complain about things being wrong in the networking industry. And I've been seeing stupid things being done for the last, what's that, 30-something years, almost 30 years. So today I'll tell you a few things done right and a few things that are still wrong in the data center space. And I'll start with a very simple question. You're a network operator, so why do you care about data centers? And then, what exactly is a fabric? And why do we have all these different solutions? And what should I really ask for? Let's start with why does it matter? This afternoon, I'll have a talk about cloud computing. And I know you had a cloud session on EuroNOG. The fact is that today, as a network operator, you have two options. Either you compete with everyone else on the price of bandwidth, which is boring, or you do something else. And cloud is the something else you could do, potentially. That's why so many operators are looking at offering cloud services. And everyone hopes this is the next big thing that will bring in money. Yeah, sure. Maybe for some. Cloud computing requires huge data centers. That's the idea. And they have to be scalable. They have to be elastic. So you have to be very flexible. And the traffic patterns in a data center have changed. Traditional web hosting, a server offering content to the users out there. Today, most of the traffic stays within the data center. So for example, for the Facebook to generate that page with the feed, with all the news from all your friends and your stupid pictures, they have to generate hundreds of requests internally. And that goes and generates hundreds and hundreds and hundreds of database requests. So most of the traffic is within the data center. Very simple illustration. Today we're talking about terabit switching fabrics. And most people have like gig or 10 gig uplinks into the internet. So you have terabits within the data center, and you have gigabits going out. No, well, not you. That tells you everything. What is a fabric? It depends on what gear you're selling and what your gear can do. So I will not go into this. These are just definitions from 3 major vendors. And as you can see, there is almost no overlap. So fabric is whatever you want the fabric to be. What you should ask for is more important. Number 1, unified storage and networking. This is a must because it reduces your cabling. Without this, you have dual cabling, you have all the problems you had before. If you don't go for this, you haven't done anything. Number 2, lossless transport. I know we all love to hate fiber channel, but lossless transport is not a bad idea. And it also helps with high volume TCP sessions like iSCSI. Because if TCP loses one packet, it goes into, slows down and then slowly restarts. That doesn't matter if you have millions of users surfing. It does matter if you have one huge iSCSI session. So lossless transport is extremely important. Next, multipathing. We had it on layer 3, always. The only question is how many equal cost paths can you use? Traditionally, it was 4. 4 is not enough. 16 is sort of OK. Optionally, layer 2 multipathing. And it's not a bad idea to reduce the latency and to have more east-west bandwidth. By the way, I was always confused by this east-west, north-south. So going out of the data center is going north. Okay? Between the servers, it's east-west. Makes sense? No. South is the server. The server is always going south. And it's good to have some control and management features like a single configuration, simplified provisioning, and things like that. So if you want to build huge data centers, you can't build them with the old methods, manually configuring switches. You have to do something else. And by the way, when you talk with the vendors, don't allow yourself to be dazzled by all the hype. Everyone will promise you heavens on earth. Think about the architectures, because software features can be added or changed. Broken architectures can't. Before going anywhere, I want to address the 3-tier, 2-tier, 1-tier stupidities. Everyone is telling you how Cisco is bad because they have 3-tier data center architecture, and we are better because we have 2-tier architecture. That's plain stupid. The only reason we had 3 tiers in traditional data centers is because we had 3 levels of speeds, like 100 meg going from the server, gig going from access layer into the core, and then 10 gig in the core, something along those lines. And we had the problem with port count. So we needed 3 layers because we didn't have big enough switches to aggregate. Today, building a 1-tier data center is not a big deal if you're small enough. Okay? You just take, let's say UCS from Cisco. It's a few hundred gig within that switching thing. And you have like terabytes of RAM in the UCS chassis. Who cares about anything more? 1 tier is good enough if you're small enough. Anyway, so what we need to go from 3-tier to 2-tier, for example, is just high-density core switches. That's all you need. But this is a hardware thing. It doesn't solve any of the problems you have. The questions like, do I need bridging or routing? Or where will I put my firewalls and load balancers? They don't change. Okay? You still have to place them somewhere. And by the way, the biggest problem that we have in the data centers, and it is not removed by going from 3-tier to 2-tier architecture, is the spanning tree. Some people think they need to bridge. Okay? I always have fun poking holes into that theory. But some people think they need large-scale bridging. And if they do it with traditional data center switches, and they run spanning tree, well, number one, they have a meltdown every now and then because spanning tree just breaks. And I guess everyone who's old enough has a nice spanning tree meltdown story. And spanning tree, by the way, blocks half of the links because of the way it works. My solution, I'm a layer 3 guy. Okay? I am a layer 3 guru from the ivory tower, I was called, by someone who was promoting large-scale bridging. So route as much as you can. Routing was invented for a reason. If you can't do that, multi-path bridging or multi-chassis link aggregation will help you. So what is multi-chassis link aggregation? It's a very simple thing. If you have 2 links in parallel and you bundle them into 1 link, it looks like 1 link, so spanning tree doesn't complain. But you can't do that if those links terminate on different switches. So every single vendor on the market has a solution where 2 switches on the top, 2 northbound switches, appear as 1 single switch to the southbound switch, so that 2 links can be treated as 1. Every single vendor has something like this, and every single solution is proprietary. Because there is no single standard covering this. So this is one of those features that we absolutely need in the data center. Everyone is doing it, and no one ever took time to standardize it. Isn't that great? And the other thing that everyone has fun standardizing, although it's, in my opinion, pretty useless, is large-scale bridging. So the idea is always the same. We have some classic bridging on the edges, and we have something in the middle that's better than classic bridging, and it does multipathing, and it doesn't run spanning tree, and it offers you heavens on earth. And the earth, by the way, is flat, okay, because we're bridging. And there has to be something special going on these edge nodes so that they can interact between the old and the new world. And there are, as always, two competing solutions. And this time, they were developed by the different standards organizations, just to make it more fun. So here is the IETF version of large-scale bridging. It's called TRIL. What TRIL does is almost routing on MAC addresses. Almost. So with TRIL, if you go into the headers, you see that you have the payload, which is the original packet. Then you have the layer 3 header, where you have the bridge IDs and the hop count. And this layer 3 header makes it routing, sort of. And then you have the outside layer 2 header, where you have the source and the MAC addresses of the adjacent, what they call R bridges. Is anyone old enough to remember routers, like 15 to 20 years ago? Ah, yes, you are. So we knew they would fail, and they did fail, and they failed miserably. And that's why no one is selling them any longer. And because routers is such a bad term, now we have R bridges. The other option, by the way, is 802.1 AQ, which is not routing at all. It's a better bridging. So they took the MAC in MAC, or the provider backbone bridging frame format, and they modified the control plane so that they don't run spanning tree, they run ISIS like TRIL does. And they compute the paths, and they use some very clever tricks to ensure that you never get loops. I mean, the way they had to go to implement loop-free routing, well, forwarding, is amazing. But supposedly they did it, and there are even shipping products using this from Avaya. Okay? So you have, as always, two competing standards to choose from. Current implementations, nothing standard yet. So Cisco was too early. So they developed the chipsets, and then the frame format changed. So Fabric Path uses something which is almost TRIL on the control plane, so ISIS and all those things. But the packet format on the wire is totally proprietary. And it uses the source and destination MAC addresses in weird ways. So they're no longer MAC addresses. They're something else. And because of that, you can't have standard switches in the middle, which you could with TRIL, by the way. But they do have active-active forwarding into this large-scale bridging matrix, if you wish. So it is better than the standard TRIL, because standard TRIL allows you to have only one single node between a VLAN and the core. Otherwise, you would have to run spanning tree. That's how bridging works. Brocade claimed they have TRIL. They were lying. I told them they were lying, and they were extremely upset. And then we agreed that actually they don't have TRIL, but it's roadmapped. So what they do have is TRIL-compliant data plane. So the packet format they use is TRIL, or so they claim. I trust them on that point. They don't have ISIS. They reuse the fiber channel code. And they're running FSPF as the control plane protocol, which obviously is far, far away from Trill. And they haven't solved the appointed forwarder, so the single entry point between the old and the new. So they have a serious problem there, and they don't support spanning tree interaction. So I was writing a few blog posts about this. There are ways to solve this problem, but you have to be aware that there is a problem and that you have to be careful. Avaya is running 8.1AQ, the Mac in Mac variant, so the good one. And they clearly admit that because they launched the product before the standard is finalized, it is pre-standard. But the data plane is right, so the hardware is OK. And they might have to do some tweaks on the control plane. And Juniper is totally proprietary Q fabric. So nothing standard in there. OK, now faced with all these crazy architectures, one has to wonder what is good, what's bad, what will survive, what won't. And I always try to step back and look at the big picture. So I will try to give you a few examples of the architectures and the benefits and the drawbacks. And I will focus on how different people solve the three-plane functionality in a typical switch. So you know you have the data plane, you have something which is between data and control plane, like MAC address learning. You have the control plane that runs STP and Trill and OSPF and what else. And you have the management plane, where you configure, monitor, do SNMP, whatever. And the question is, in a particular architecture, what is centralized and what is distributed? And the first one we have is what I call business as usual. So traditional switches, each switch is an independent unit. It has its own management plane, so it has its own configuration. It has its own data and control plane, obviously. And things like this, examples are Nexus from Cisco or well, almost any switch from almost any vendor, apart from a few exceptions. What are the benefits of this? Well, we know how it works. We've been using this for ages. We know it scales if you do it on layer 3, because internet is built this way. And it scales better, but the problem is it scales no better than what we have today. So if you think you need bridging, you have a problem. An example is the virtual port channel on Nexus switches. So it appears as a single box to the poor guy down here. And the reason it appears as a single box is because all the control plane packets from this guy are sent to the same routing engine, the same supervisor. So you have two independent boxes, but only one of them talks to the guy connected to them. So they're independent, they work independently, but they agree on who will represent the both of them and talk spanning tree and LACP with the guy down here. And by the way, VPC is one of the few solutions that can do active-active forwarding into large-scale bridging. As I said, everyone has a solution along these lines, and I'm just listing the vendors that I know of. Cisco and Avaya are the only ones that can also offer layer 2 multipathing because they have those solutions that I mentioned before. And Brocade did go a step further, and I'll show you what they're doing. And by the way, these are the things you have to check. Some people implement multi-chassis link aggregation in a way that one link is active and one is standby. So how is that different from spanning tree? It's not. Some people tell you, yes, you can do link aggregation, but you can't run spanning tree on it. OK, so how will I prevent loops in my network? Thank you, Mr. Vendor. And some people can do off VLAN functionality in active-active mode, like layer 3 forwarding. So for example, the Nexus switches, if this is a layer 2 switch and they're both layer 3 switches, and they do VRRP or HSRP or whatever it is, the packets will go straight off into the internet. Whereas with some other vendors, only one of these guys would do layer 3 forwarding, and if the packet lands on the wrong one, it goes over here and then off. So these are the 3 things you need to check. Brocade has a really good product, by the way. Once you get past being upset that they tried to mislead you about Trill, it's a great product. Well, automatic trunk negotiations, things like that, okay, they like to emphasize that, but you know, that's obvious. What they do have, and it comes from Fiber Channel because this thing is built on their Fiber Channel products. So this is Brocade, this is not Foundry. Okay? They have optimum load balancing. They're scheduling the packets in a very smart way so that a single session, a single TCP flow can go over both links in an Ether channel. How is that for a wow? I mean, when I've heard that, it was like, wow. And the link aggregation can be terminated on any 2 boxes in the whole fabric. With Cisco, with any other vendor, you always have boxes working in pairs. And you can terminate the channel on both boxes in the pair. With Brocade, you can terminate the channel on any 2, or now they'll go to any 4 boxes in the fabric. But they also promised unified management and who knows what else, and it's not there yet. Each box is still independent, but they do have some cool features. Next architecture, what I call Kilt. It's a patchwork of independent devices. So here you have independent control and data planes, but you have shared configuration and shared monitoring, which is, by the way, very cool, because you get one configuration to compare against the previous state. Okay? So you're not managing hundreds of configurations from hundreds of devices. You're managing one configuration. You have one management IP address. You do show, and it collects data from different boxes and gives you the show printout. You do SNMP counters, and it looks like one device. Examples, Cisco's UCS. The UCS manager does this trick. And Juniper's virtual chassis, the stackable switches, even though they look different, they do run ISIS internally, so they actually use this model, which is more scalable than what some other people are doing that have a single control plane. I would really love to see this work on layer 3, because layer 3 configuration would be interesting. Most implementations like Cisco UCS or Juniper's virtual switches are layer 2, so it's easy to do this on layer 2. Next one, some people have this great idea that I have multiple switches, but they have a single brain, like the Borg Queen. Okay? So you have, of course, you have shared configuration because you have a single control plane. You have distributed data planes, and you have one set of IP addresses because it's one control plane, one set of routing adjacencies, and so on. Examples, Cisco's VSS, HP's IRF, Juniper's XRE, or Nexus 1000V, for example. Most stackable switches also work this way. The only problem with this thing is it doesn't scale. The most anyone managed to do on a reasonably sized switches are 4 switches. 4 switches with a single brain sort of works, sort of. If they're large enough, it's 2 switches. Okay? And of course, there are a lot of problems. So, is there any Star Trek The Next Generation fan in this room? No? Me, yes. So, you know what happens when a Borg loses connection with the Borg Queen? there's a problem. So the same thing here. If numerous switches have one control plane, then if you lose connection to the control plane, you're lost. And you don't know, have you lost the connection or has the control plane died? It's the classic partitioning problem. What shall I do? And there are different ways of handling this. And in most cases, the poor guy that loses the connection to the control plane says, OK, probably he died, so I'll take over. And then you might have active-active split brain, so two people behaving like one and being schizophrenic. And therefore, every single solution like this has a mechanism to detect split brain. And when they do, one of the poor guys has to sacrifice himself and kill him so that the other brain takes over. So whenever you get a partition and then merge, someone resets. And you know that a reload of a high-end switch can take minutes sometimes. Cisco's VSS and HP's IRF are the examples of this architecture. And you can get into great arguments with HP people or with Cisco people telling you how their solution is better than the other. And these are just minor differences. I mean, the architecture is different. And the question is like, OK, if we get into split brain, who will reload, the previous master or the new master? Like, this is important, right? So Cisco obviously has two catalysts in the VSS, and HP claims that IRF is a universal solution for any problem. But so far, they managed to combine two high-end switches or four stackable switches into a fabric. And there is a mid-range campus switch, which will be able to have 4 campus switches in a fabric. It only has to ship. It's been promised, I don't know, summertime or something like that. It still isn't available. Juniper went an extra step. And I was joking and saying that, you know, the brains in the switches were not big enough. So they added an external routing engine. So you want to combine 2 high-end Juniper switches into this Borg mode. You have to add 2 external brains. And then the brains in the switches are turned off, and one of the external brains takes over. Apart from that, it works well. But it's a lot of money, obviously. Then we have other interesting architectures like what I call tendrils. Single control plane and centralized data plane. So this is, for example, what Cisco has with the port extenders. You have the port extenders that connect to the upstream switches, and the port extender has no local switching. So all the traffic goes through the controlling bridge and back. This is great for north-south traffic. It stinks if you have a lot of east-west traffic. And then the last one that Greg Farrell will talk about in a minute is what I call the big brother. So the idea is that a controller inspects the first few packets in a flow, and then figures out what to do with the flow, and then downloads the forwarding entries into individual switches. So this is something like we do with wireless controllers, or something that Cisco does with its VSG, Virtual Security Gateway, or this is what you can do with OpenFlow. You think this is a good idea? Is there anyone in the room who had to troubleshoot multi-layer switching on a Cat 5000? So you know how it works. And last but definitely not least, there is the Q fabric. And I wanted to make a Q joke here for the Star Trek fans. So what they do is something totally different, and it's actually pretty cool. So the elements of the Q fabric are the interconnects, which are very, very high-speed switches. And they can be high-speed because they don't do layer 2 or layer 3 switching. They do switching on some internal format. So it's like MPLS P routers, if you wish. And the nodes are the actual layer 2, layer 3 switching that do the lookup and decide where the packet needs to go, attach a label to the packet, send it through the interconnect. By the way, interconnect is like 3-stage class tree. So a lot of switching elements connected together in the right way, so you get awful performance. It's like, sorry, awesome. Not awful. So it's like 10 terabit per interconnect. And you can put 4 interconnects together and load share between them from the QF nodes. So you have 40 terabits switching bandwidth that behaves like a single switch. That's cool. And the control plane is totally separate. So you have to build an extra gigabit LAN with their stackable switches to connect everything together on the control plane. So it's out-of-band management, like we had with ATM or Frame Relay or Sonnet. And you have at least 2 directors, which are like the external brains of this thing. And when they launched this, when they were talking about this, I went like, OK, how do you want to scale the control plane to 100-something switches? It's never been done before. I don't think you can do it. They can't. And what they actually do is really smart. They group these switches into node groups. A switch can be independent node group, or you can combine 2 of them together, and then you have things like multi-chassis link aggregation. Or you can combine 8 nodes into a network node group, and it offloads the control plane functionality to the director. So most of the switches stay independent, and where it matters, you combine them together and you offload their brain to the director. So it's like XRE that I've shown before. So this is this, and they do have one-hop lookup. So the ingress QF node does the lookup, and then the packet flows across the fabric with no additional lookups. So they get, because of this, they get something like 5 microsecond end-to-end across the fabric. And single CLI, single IP address, single configuration file, single management entity, single set of SNMP counters, single set of show commands, which from the management perspective is really cool. OK, now you know as much about these architectures as I do. So what do you want to do when you deploy your next data center? Well, number 1, don't rush. Just because something looks nice doesn't mean that it will perform well. Wait for all these new ideas to settle a little bit. And evaluate what you actually need. And don't talk to the server people, because they will tell you they need flat earth. Talk to the business people. Hey guys, what is it that our business needs to make more money? And let me help you translate that into what my network needs. So try to get as close to the business people as possible. And buy according to what your business needs are, not according to how fancy or nerdy it is. This always works. And evolution is better than revolution. You know that. So don't rip out your whole data center and replace it with something brand new. For example, QFabric, yeah, it's a good idea for a total greenfield deployment. So you need to build like a Hadoop cluster with 1,000 servers. Yeah, consider QFabric. You need to upgrade your data center? No. And specific to the fabrics, some of you know how much I love Gartner. And even Gartner agrees with me that large-scale bridging is dead on arrival. Why? I'll tell you this afternoon in the cloud computing networking session. We don't need it anymore. It's gone. It's dead. So I do feel sorry about the vendors that invested so much money into it. But when Cisco launched VXLAN with VMware, I told them plain and clear, hey guys, you just killed Fabric Path. They went like, no, 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 no. But it is dead. FCOE, some people might disagree with me, but it's a must. If you have fiber channel, if you need to support fiber channel, FCOE is a must. Otherwise, you will stay in the old world and you have dual cables and dual infrastructure and dual everything. Lossless Ethernet is a must. If you're buying new boxes today, they have to support lossless Ethernet. iSCSI will thank you. Even if you're not running FCOE, iSCSI works way better over lossless. And revisit some old designs. Closed networks were invented for voice switches in 1940s. And you can build a data center closed network with, for example, 4 stand switches. Well, now it's Dell. Pretty low price, pretty good performance, a bit more management overhead, but you can get reasonably good switching bandwidth out of simple layer 3 switches. When this presentation will be published, you have a number of links and blogs and podcasts that you can listen to and get more information. And now I think, am I over time? No. Wow. So whatever questions you might have, I'll try to answer as many as possible until they tell me to stop. And I'll be outside anyway, so if you need more information, just find me.
Lossless Ethernet.
Yeah.
Can you go a bit into this? How this?
Lossless Ethernet idea is very simple. You do it on hop by hop. So the technology you need is called the priority flow control. It's the same thing like the pause mechanism you had on gigabit and 10 gig Ethernet, where the receiver tells the sender to stop. You remember good old days, X on, X off on async terminals? That's it. So the sender is sending, the receiver is running out of buffers. The receiver tells the sender to stop. And it has to tell the sender to stop well in advance so that when the sender stops, the receiver still has some buffer space left. This exists in gigabit Ethernet. But the problem is that in gigabit Ethernet, it is on or off. So you can't do this for specific traffic classes. What we would like to have is, let's do this for FCOE and iSCSI, but not for regular web surfing, because that doesn't matter. And PFC is just that. It's the pause mechanism for 8 priority classes.
It says to stop or to slow down?
It has to stop.
Okay.
It's on-off. So the question was, does it have to stop or can it slow down? No, it has to stop. The slowdown mechanism is QCN, another standard, quantified congestion notification, where any switch in the network can tell the sender to slow down. It only makes sense if you have lots of switches in the row, but as Gartner says, large-scale bridging is dead, so QCN is irrelevant. And now they're telling me I'm over time. So any more questions you have, meet me outside.